Hello guys, this is 11.1 parametrization of plane curves. So let's talk a little bit about what a parametrization is. So normally we have some function y, which is f of x, where y is the dependent variable and x is the independent variable, and the value of y depends on the value of x of our choice. What a parametrization is, instead of having a regular function like f of x, our function for x and y on the xy plane is actually based on some value of t, right? So x is now a function of t, and y is now another function of t. And then these two functions will determine what your x value and y values are based on the t values of your choice. And then the t in this case, most of the time, it's going to be in time, right? So you can think about driving, right? Let's say you're right here, right? And then you're maybe on a scooter or something, right? And then your traveling path is not going to be nice like a function f of x, but instead it will be more like a parameterization of function, right? So for example, right here, you are at x of 1 and y of 1, right? So what these tells you is where your x value is at time 1, or and what your y value is when time is equal to 1, okay? So let's take a look at the definition, right? If x and y are given as functions x equal to f of t and y equals to g of t over in time interval I of t values, then the set of points xy is equal to f of t and g of t, defined by these equations, is a parametric curve. The equations are parametric equations for the curve. Okay, so unlike our regular functions, y is dependent on x. Here, x and y, or f and g, they are actually two separate functions that is based on the same variable t. Okay, so let's take a quick example. Take a look at a quick example. Let's say x is equal to sine of pi over 2t, and y is t. Okay, and let's attempt to build a table for this, right? And then what we will have is something like this, right? So t is equal to 0, and thus x is 0 and y is 0. When t is equal to 1, x is equal to 1, y is equal to 1, and so on, right? We have freedom over the t values, right? Because t value is our independent variable, right? Where x and y are both dependent on the value of t. And what's going to happen when we graph this is we will have a picture that looks like this, right? So notice that this graph does not represent a function, right? Because we are not talking about a regular xy plane function or Cartesian function where y is dependent on x. Here we're looking at two separate functions, f and g, and each one of them represent x and y respectively. So this is why we see weird looking graph like this, right? And what this parametrization is telling you is, let's say you start at 0, 0, right? As time goes on, how are you going to travel on the xy plane, right? And that's what the parametric equations are saying. All right. Okay, so let's try another one from scratch. Right? We have x and y per our parametric equations, and our intervals is from 0 to 2 pi. We want to graph them. All right, so let's do this. Build a table, right? T, x, and y. Okay, and let's break it down into just the quadrantal angles. 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so 0 for x, so a cosine 0, that's a, and sine 0 is 0. Pi over 2 cosine is 0, and sine the power of 2 is 1, so that's a. Pi is negative a, 0. 3 pi over 2, that's 0, and negative 1, that's a negative a. And then back to 2 pi, which will be the same thing, that's a and 0. Okay, so let's see what we have. Okay, have our xy axis here. All right, so at t0, we are at position or coordinate a0. All right, so let's say here, a0. It's when t is equal to 0. All right, and when t is pi over 2, our position is at 0 and a. So 0 and a is right here. Right? 0 and a when t is pi over 2. The third one, when t is equal to pi, our position is at negative a and 0. All right, so negative a and 0 when t is equal to pi. Okay. And then 3 pi over 2, when t is 3 pi over 2, xy positions are 0 and negative a, 0 and negative a, right here. Right, t is 3 pi over 2. Right, and when we are back to 2 pi, we will go back to a0. So here it's also t equal to 2 pi. All right, so let's trace the path. Right, so as you may know, this actually looks like a circle, right? Like a unit circle. Well, except it's not unit circle because radius is a. All right, so it's gonna go like that. T equal to 0. Okay, that's really bad. Okay, I'm gonna try my best to graph this here. Okay. All right, so there you go. Right, that's our parametric curve. And one thing you want to do is also you want to include the direction of traveling, direction of the path, right? So t0 is here, right? And then we actually is traveling counterclockwise. So you want to add arrows somewhere on here to note that the direction you're traveling. Okay. You can see that this t here actually works like theta, and then x and y are look like sines, right? So that's another way to represent a parametric curve in this example. Okay. All right. Next, let's look at the relationship between parametrization and Cartesian functions. Right? So parametrization meaning we have x of t and y of t, right? We have two different functions representing x value and y value. And the Cartesian function is the regular one where is y is equal to f of x, right? The common one that we know. So we want to see if we can relate these two together or convert between these two. All right, let's look at a quick example first. Let's say I have a parametrization, parametric equations, x is equal to radical t, and y is equal to t, and then t is non-negative, right? So what we can do is, we know that y is equal to t, y is equal to t, right? And t is also equal to the square root of t quantity square, right? And we know that square root of t is equal to x, so that is actually equal to x squared, right? So here we can say that the parametric equation that is given to us can also be translated into a Cartesian function, which is in the form of y equal to x squared, or f of x equal to x squared. Right? And then if you take a look at, if you try to graph these two parametric equations, you will also get a parabola, right? But it's not the whole parabola, it's only the right-hand side of the parabola because we have a condition here, t is greater than or equal to 0. Okay, so going from parametric equation to Cartesian function, meaning in the forward direction that we just did, is pretty easy, right? You can just try to smash the two functions together using t, and then represent y with x. But to go backwards, to go from Cartesian functions to parametric equations, that is going to take some work, right? So what we're going to do is we're going to introduce the first technique, which is called natural parametrization. All right. So what the natural parametrization is saying is, if you have a graph of any given function, let's say y is equal to f of x in the Cartesian form, this can also always be written as, when we're going to pick x, the first parametric equation, I'm just going to let x be equal to t, right? It's like substituting a variable, replacing one variable with another, right? And then y, in this case, would just be f of t, right? Very straightforward, very simple. Okay? And the domain of the parameter in this case is the same as the domain of f, right? So they will have the same domain as f of x, right? So this is the natural parametrization, right? It's just replacing x with t's, and that's it. Okay, so let's try, a very simple one. Let's say we want to parameterize y equal to x squared. All right. So first, natural parametrization says, okay, I'm gonna pick x equal to t. Right. That means y is equal to what? T squared. And done. That's it. Right. Well, I should say, actually, maybe not skip a step. Y is equal to f of t, which will be t squared. Right? And done. Right. And that's pretty nice, pretty straightforward. But of course, sometimes we can do a little adjustment in the variation on the x part, right? Instead of picking just t, maybe we can pick something else that'll make it a little easier and make it look a little nicer. Okay, let's look at our first non-natural parametrization, which is trying to parameterize a line through the point AB with slope m. Right. So in the Cartesian equation, right, we can use a point slope formula. Right. And then the line that goes through the point AB with slope m would look like y minus b is equal to m times x minus a. Okay. And then we're trying to parameterize this equation, right? This Cartesian equation. So let's see. We're going to start here. Now, instead of picking x, if we pick x minus a, if we pick t to be this whole thing in the parentheses, then we can actually save some time, right? So if t is equal to x minus a, then I can say that x is equal to t plus a, right? Or a plus t. That's pretty good, right? Therefore, the whole original equation can be written as y minus b is equal to m times t, right? And there you go. We can just add the b over. We get y is equal to mt plus b. Right? And the set of parametric equation will represent the line, the straight line that has the same property, right? Where it's a straight line going through AB with slope m. All right. And before we end today, I actually want to talk to you guys about something called the cycloids. Now, cycloids is a special path that is formed by rolling a circle on a straight line, right? But in the historical view, the cycloid was actually first defined as like a swinging pendulum, and then the path of that swinging pendulum. Okay, so let me show you a picture real fast, and hopefully it can be understood. Okay. All right, so assuming that we have a circle that sits on top of the x-axis at 0, right? And then it's going to rotate to the right. It's going to roll to the right, right? So it's going to roll like this, right? And then we're looking at one fixed point on the circle, and the path that this point makes is called the cycloid, right? So we see like two little bumps like that made by looking at the fixed point of the circle when it rolls around. And this path is called the cycloid. And we're going to learn about what their parametric equations are, and how do we work with it, what type of properties it has. Okay, so let's take a look. All right, so we're going to look at the cycloid, or meaning we're looking at this fixed point, right, at a certain time, right? And we're going to find its x value and its y value. Right, so if we look at the x value first, right, this amount is basically just a times t, right? Your radius multiplied by the time it's traveled, right? If it's 1, then you could travel 1, you travel t. If it's a is 2, then you travel 2, right? Like this, right? 1, that'll be 1 times t, and that'll be 2 times t, right? And then when you don't hit a full t, then it's going to be found by using cosine, right? Cosine of theta, which is this distance right here. Right. Let me get a different color. This distance right here, right? Which can be found by a times cosine theta, right? And then that's the x value, right? At plus a cosine theta. Now, of course, we're not going to use theta. It's going to be t, which represents the rotation. In a sec, right? And then the a value is just the y value is just the vertical distance, right? So you have the radius and then plus a sine, right? If it's below, it's less than radius, and a sine is going to be negative, and so on. Okay, so we're not going to get into details on how. You don't have to worry about the details on how we came up with the parametric equation, but I do want to give you this set of parametric equation, and this is the one you want to know. Right, the cycloid curve has the parametric equation, right? X is equal to a times t minus sine t, and y is equal to a times 1 minus cosine t. Right, now there are actually a lot of work done in here, right? But we're not gonna worry about that and bore you guys with that. So we can just use this as it is, and we'll have some fun with it. Now, in the textbook, they actually talk about two different properties of cycloid called the brachistochrone and tautochrone. Um, they are more of a physics and engineering term in terms of the property of cycloid. Not where I'm actually not going to cover that in our class, but if you're interested, it's in page 668 of our textbook. And for those of you who have understanding of cycloids and maybe properties of those, feel free to take a look at that. And yeah, maybe you will find them interesting. Okay. So to sum it up, basically in this section, we're just introducing parametric equations or parametrization of plane curves. Right, we learn about how to graph parametric curves, and how to perform converting between parametric equations to our Cartesian functions. Okay, and there are many different approaches. So there you go. That's it for today. Thank you guys very much, and I'll see you next time.